The process of developing a new product is divided into several stages. These stages range from the generation of new concepts to the actual manufacture and launch of the product. In later stages, the product can also be subjected to revisions according, for instance, with feedback provided by the consumers. The new product should be carefully analyzed and tested in the initial stages of the product development process, since modifications made to the product at these stages have a higher impact and lower costs. In later stages, during production for instance, the costs related to modifications of the product are reflected in significantly higher costs and time to market. Therefore, the use of virtual tools, such as computational fluid dynamics or the finite element method, allows the project team to perform a preliminary screening and various alternative designs, and thus avoiding additional physical prototypes or modifications of the product at later stages of the design process. For instance, computational fluid dynamics, or CFD for short, can be employed to analyze the flow of air due to the heat, ventilating and air conditioning system, or the noise generated due to turbulence on the flow caused by a moving car. The majority of the flows in industrial applications have a turbulent behavior. A turbulent flow is irregular, random, and chaotic, and is composed of eddies or vortices at different scales. There is a flow of energy from the largest turbulent scales to the small scales. At the large scale, kinetic energy is removed from the mean flow, and the eddies are unstable and break into smaller ones, transferring energy to smaller scales. The eddies at this scale then break up into smaller eddies, and so on. At the smaller scales, energy is dissipated as heat. This process is known as energy cascade. The instantaneous velocity of a point in the turbulent flow shows small amplitude and high frequency fluctuations due to small eddies, and high amplitude and low frequency fluctuations due to large eddies. This results in a velocity profile with fluctuations of different frequencies. There are different approaches that can be used to represent the turbulent behavior of a flow. In direct numerical simulations, DNS, no turbulence model is used, and the unsteady 3D Navier-Stokes equations are solved directly for all scales. This approach requires very dense meshes and short time steps, make it very time-consuming. Therefore, this approach is typically only used for very simple academic cases. In scale resolving simulations, SRS, with approaches such as large eddy simulation or LES, the smallest turbulent scales, which require small length and time scales, are left unresolved and are accounted for using specific models. In this way, only the medium to large eddies, which are anisotropic, are computed explicitly, allowing the analysis of flows with high Reynolds number. When compared to DNS, coarser meshes can be employed, but the computational cost is still high when compared with other turbulence methods. Therefore, many industrial and academic cases require even simpler models. In these models, not only the small length and time scales, but also the intermediate to large turbulence scales must be filtered out to obtain a set of equations to be used. In these models, the flow is described statistically by the mean flow velocity and the turbulence quantities. Doing a time average over a reasonable time period, the turbulence fluctuations are separated from non-turbulence quantities, leading to the so-called Reynolds average Navier-Stokes equations, or RANS. RANS models only represent the mean behavior of the flow, but for many practical industrial applications, this information is enough. However, due to their nature, RANS models are not able to capture the fluctuating characteristics of the flow. For instance, in order to determine the noise generated due to turbulence effects, such as air flowing along the body of a moving car, it is necessary to capture small pressure fluctuations of the flow, which cannot be done with Reynolds averaged models. As such, scale resolving simulations must be employed. The use of such models in preliminary analysis during the initial stages of the development of a new product may not be feasible in standard workstations due to the higher execution times required. However, the information that can be extracted from such numerical simulations can be extremely useful when developing a new product. In these cases, the use of high-performance computing HPC, sometimes also denominated as supercomputers, can provide significant advantages. In a general way, HPC combines the computational power of hundreds or thousands of compute nodes in order to solve complex computational problems in a lower amount of time. Compute servers are networked together as a cluster. The software or algorithm necessary runs in several nodes simultaneously. An HPC also has a storage system that receives and sends data to the nodes. As an example, let's analyze the noise generated by the airflow on the ducts and outlets of an HVAC system of a car. With the evolution of vehicle motorization and the substitution of traditional combustion engines by, for instance, electric ones, the noises that were previously masked by the engine noises are now more perceptible. These noises can negatively affect the perception of comfort of the user. Therefore, the use of CFD simulations may help the engineering team to optimize the ducts and outlets of the HVAC system in order to reduce noise. To demonstrate the advantages of using HPC, a simplified geometry of a duct and outlet was considered. Because we are dealing with a CFD simulation, the interior of the duct and a fraction of the car cabin are discretized using a three-dimensional mesh. In this case study, the Navigator HPC from the Laboratory of Advanced Computing from University of Coimbra was used. Each computing node used is composed of two 20-core Intel Xeon Gold 6148 at 2.4 GHz and 96 GB of memory. The results were compared with a computing workstation composed by an Intel Xeon Gold 6128 CPU at 3.4 GHz with 64 GB of RAM running a 4-core. The analysis is divided in 3 steps. In the first step, using the steady-state run, the speedup of the simulation with an increasing number of computational nodes was analyzed. The maximum speedup possible corresponds to a linear speedup, which means that increasing the computing cores by 32 would result in a speedup of 32. However, there are parallelization limitations as well as hardware limitations. For instance, in parallel computing, there must be a communication between the different nodes. By increasing the nodes, the communication between them also increases, and there is a point in which there is no gain in considering a higher number of computation nodes. For the present case, increasing the number of cores to 64 leads to a speedup of approximately 38. This represents a reduction of the execution time of the simulation by a factor of 12 when compared with a standard computation workstation running on 4 cores. At the end of this first stage, the average behavior of the flow is determined, and it is now possible to move on to more complex calculation. At the second stage, a transient analysis is performed until a fully developed flow is obtained. In a transient analysis, the problem is divided in time steps. Due to the nature of the problem and the employed models, a very small time step is required. Together with the fine grid necessary, this results in a total of about 10 trillion equations that must be solved. For a sense of scale, 10 trillion seconds is the time that Usain Bolt would need to run full speed to Mars and back about 1,200 times. The third and final stage also results in a similar number of equations. Using HPC resources running on 64 computation nodes, the execution time of the second and third stages took about 6 days. In a standard workstation with 4 cores, the same simulation would run for 74 days. It is now possible to see the fluctuations of the pressure and velocity fields, which is a necessary condition to be able to determine the flow-generated noise. Clearly, there are significant benefits when considering high-performance computing, especially in the context of small or medium enterprises that do not have available in-house the processing hardware required to solve complex and time-consuming computational models. These companies are the ones that should be able to have higher benefits when using HPC by optimizing their processes, increasing productivity, and reducing costs related to new product development. The case study presented in this work is only one of the possible applications of HPC in the industry. With concepts such as big data, Internet of Things, and digital twin, the use of HPC can give the necessary competitive edge to small or medium enterprises.